best thing, got the best thing, only thing I'm missing. You got the best thing, got the best thing, and it's...
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to the topic of chemical equilibrium. So a reaction at equilibrium is written like this, where we go from reactants going to products, with this arrow that goes forward and backwards. So in this case, the concentration of the reactants and the concentration of the products do not change, so remain the same. So when I put these brackets around whatever reactant or product I'm talking about, remember that I'm talking about concentration. So at a molecular level, reactants are still forming products, and the reverse reaction of products forming reactants is also occurring. So under the same conditions, reactions at equilibrium have the same ratio of products to reactants. This ratio is called the equilibrium constant. And this is written as Kc. And so if we have a reaction at equilibrium, such as A plus B goes to C plus D, whatever these molecules or compounds are, where these small alphabetical values, A, B, C, and D, are the stoichiometric coefficients of the balanced reaction. So it's a number, basically showing how many of each different entity you have. Okay, so then in this case, Kc, the equilibrium constant, which means that the ratio of products to reactants is the same, can be written as the concentration of C to the power of small c, which is the coefficient, the concentration of D to the power of the coefficient, and the reactants on the bottom. So basically, it's products over reactants, but looking at it from a concentration point of view and also taking into consideration the coefficients. So now I can show you different calculations in which we use Kc. So let's try an example. Calculate Kc for given equilibrium concentrations, where in this case, we have nitrogen gas mixed with hydrogen gas, H2, at 500 degrees Celsius to produce ammonium. And then at equilibrium, the concentration of N2 is 0.305 molar. And remember that this unit molar equals moles per liter as a unit. And then for H2, it's 0.324 molar. And finally for ammonia, it's NH3, which is 0.796 molar. So this is all the information that's given to you in this problem, and they want you to figure out what the equilibrium constant is. So first of all, let's write out the equation. N2 is mixed with H2 to give NH3. So we have N2 plus H2 gives ammonia gas. So the first thing you always need to do is balance a reaction, right? So we have two nitrogens here, but only one nitrogen here, so we have to put 2 right here. And now we have 6 hydrogens here, but only 2 here, so we have a 3 here. So these are the coefficients, and this is very important since we have to take that into consideration for the equilibrium constant equation. So we have 1, 3, and 2 as the coefficients. So now the Kc is going to be the concentration of the products over the reactants. So we have NH3 is the product. Don't forget the coefficient, which is 2, over the reactants, where we have N2. and H2, don't forget the coefficient, which was 3. And then we just plug and chug. We basically put in the concentration values that were given to us. So 0.796 squared divided by 0.305. And all of these are in units of concentration, so molar. So everything's going to cancel out. 0.324 cubed. And when you plug this into your calculator, the answer is going to be 61.0. So for this particular reaction of nitrogen gas combining with hydrogen gas to produce ammonia, the Kc, or the equilibrium constant value, was 61. As you can see, this value is going to change based on the ratio and the concentration between the reactants and the products. So we just figured out that the equilibrium constant for this equation, combining nitrogen and hydrogen to give ammonia, was 61. But we can also do the reverse reaction. So in this case, the reverse is merely 2 NH3 dissociating to nitrogen gas and 3 H2. And what I wanted to show you here is that when you change the denominator and the numerator in the Kc equation, so now the products are N2 and H2 and the reactants are NH3, we basically rewrite that equation. So now we have N2 H2 cubed on the top for the products, and now we have NH3 on the bottom. So basically the relationship between the forward and the reverse reaction is that it's going to be the inverse. So this is going to be 1 over 61.0, which is 0.016, and this is called 1 over Kc, or Kc to the power of -1, and it's the inverse. So what I'm trying to say here is that the forward reaction and the reverse reaction are related to one another, and that the reverse is the inverse Kc of the forward reaction. So chemical equilibria with all reactants and products in the same phase are called homogeneous equilibria. So this means everything in the same phase. And what I mean by same phase means everything is in the solid form, the liquid form, or the gaseous form. So in this case, all of these guys were gases. When you have more than one phase involved, then we're talking about heterogeneous equilibria. And basically, molar concentrations of a pure substance, so by that, a pure substance is a solid or a liquid, does not change in a reaction. So let me reiterate that. Basically, for pure substances such as solids and liquids, the molar concentration does not change in a heterogeneous equilibria. So what that means is the solids and liquids are not included in the equilibrium constant. So let's do an example of that. We have calcium hydroxide, which is a solid, and this is breaking up into the two salts, calcium 2+ in aqueous form, plus 2 OH- ions, aqueous. And so when we write out this Kc value, or the equilibrium constant, we're actually going to not include this solid calcium hydroxide, because in a heterogeneous equilibrium, we do not include pure substances. So Kc is merely going to be calcium 2+ OH- squared, because of this coefficient right here. And so basically, calcium hydroxide goes to calcium and hydroxide, but it is not involved in the actual equilibrium reaction.
You got the best thing,